I have been deliberating this video with an intuition that I may give more insight into the field of quantum computers, and it is always relevant to make a comparison between the classical computers and quantum computers. In case of classical computers, we all understand that every kind of operation undergoes through zeros and ones. We call them bits. So the mechanics involved in classical computers is purely based on the switching technique, where you can have only two states. You can either have an on state, or you can have an off state. So everything, every process, every kind of process that goes on in a classical computer, it happens by virtue of stepping either 0 bit or 1 bit. So the choice here is very constrained. I mean, this is the only way that the computers based on this technology can operate, can execute their operations. On the other hand, when we go into the domain of quantum computers, a quantum computer is not a clean reality right now in the modern world. But people are working, and people are making all possible efforts to design and operate a computer which works on the principles of quantum physics. Now, if I have to start with some argument here, you can see that there is a rat in this photograph, and this rat has to attain its prey, and the prey is over here, and in order to reach to to the prey, the rat has to experiment all possible paths that will lead to the prey for the rat, and all these paths are either in terms of zeros and ones. So that's a demonstration of a classical computer. This is how a classical computer operates, because a classical computer can operate only between two states, zeros and ones. So the rat has to make use of all possible paths in order to reach the destination that the rat has on the other corner of this page. Uh, but if the rat if we track down this system in a very quantum domain, uh, because in quantum domain we have a different state of action. What that action is all about, I mean, suppose I take an atom can have it can have a spin in upward direction, it can have a spin in downward direction. So you can say, you can choose as an argument that the upper state will refer to the spin up, and the lower state will refer to the spin down. So one of the two states can be referred as one, and the other state can be referred as zero. But at the level of atoms, the things are different. This atom can have infinite states. It can have infinite number of orientations. Now, the atom is not confined to the two-state problem that we have in case of classical computers. In classical computers, we are very well aware about that there are a lot of constraints, and and the work has to be done via only two states, 0 and 1. However, if we shift it to a quantum system probably has infinite number of states. Now, if I make a comparison between the classical bits and the quantum bits, there's a hell of difference between the two states. In classical, you have only these two decorated states, 0 and 1. But in quantum particles, but in quantum systems, there are all possible states that an atom can be in. Now, if I quote the same example for this rat, if I choose this photograph as a quantum system, now the number of paths that have been shown in this picture, not only these number of paths the rat will choose, the rat will be at the same point of time, it will have infinite number of paths. The rat will be in infinite number of states at the same time, and we call this simultaneity. That means if I choose this rat as a quantum particle, this rat will remain, will access all the infinite paths that will lead to the food that the cat has to attain at the end of performing this kind of job. And what is most important here is that it's the intuition here is totally something that goes against the preferable senses a human being has, because we cannot think of a person being at same time at many places. Suppose I'm sitting in this room, it doesn't mean at the same time I'll be present somewhere else outside this room. But that's not the case when we go down to the quantum systems. In quantum systems, the particle is simultaneously at the same instant of time operating different number of states, is present in different number of states. So what's going to happen if this photograph is replaced by a quantum computation, whether the rat is an electron or a photon, and it has to attain its destination at its prey. So if this system is a quantum mechanical system, at the same time the rat does not have to use all zeros and ones and all possible paths and finally reach to its destination. No, that's not the case. The rat will be in all those possible paths that will lead to the destination, and the rat will have to choose one path, which is the best path that will take the rat to its destination. Now, you can see this is a photograph of a quantum computer. This is American quantum computer, and Americans are working on it. And it looks a very, very huge cylindrical bulge, and lot of pipes roaming around it. This whole system, whatever is visible here on the top, these are the pipes that are making sure that the quantum system is basically the box at the bottom of this whole giant thing. We have a quantum computer here. Now, what these pipes do, they make sure that the temperature at this quantum computer, which is at the base of this bulge thing, they have to make sure that the temperature that is surrounding this system is very, very close to absolute zero, because the thing that I was talking about, being an electron in multiple states at the same time, to maintain this kind of condition, there should not be any sort of disturbance. Even sneezing in a room where this whole setup is may disturb the quantum system. So, in order to make sure that the system is undisturbed, the quantum computer has to be kept at very low temperatures, and this quantum computer, in this case, the particles that make an action in order to make operations, these are, or this is an electron based quantum computer. So Americans are working on a quantum computer which is based on the motion of electrons. And if we move on, the other part of world, now this is a Chinese quantum computer. Now Chinese people are manufacturing, or trying to design a quantum computer based on photons. So they are not dependent on keeping the temperature of the whole system very close to absolute zero. So this thing can execute at the very room temperature. But the complexity of, you can see that the photograph is itself showing that how complex the design of a computer, of a quantum computer is based on the principle of photons, because they have to use a large number of mirrors, and they have to choose all possible angles at which these mirrors are kept, and to make the operations possible, and to make the computations possible, the computations that they're looking for a quantum computer to perform. Now, another important thing is that in case of the American quantum computer, the particles that take part in the execution of computation or electrons. And in case of the Chinese quantum computer, the particles this is purely based on optical activities, the photons that can make computing and at the level of quantum states. Now, to move on, in classical computers, we have transistors performing their job, and all of us are aware about Moore's law. And what Moore's law says that after every 18 months, the embedding of transistors on a chip goes on doubling. So this thing has remained there for a long period of time, over 100 years. But now the stage has come when Moore's law is already at its saturation point. Because once the number of transistors that have to be added in a domain of 5 atoms will certainly have different kinds of implications involved in it, because quantum effects will come in action, where Heisenberg's uncertainty principle will make its role, exclusion principle will make its rule, and there are possibilities of many kinds of short circuits that are going to happen if the systems are treated classically, and we try more embedment of transistors in a very short range of atoms. So what a transistor does, a transistor is basically a modifier. I mean, if you make use of transistors in making any sort of computations, the job of a transistor is to modify the flow of electrons or holes. And in case of Chinese quantum computer, the we don't have the transistors that work on the basis of flow of electrons and holes. We have optical transistors. So that's why in case of quantum computer that's being built in China, it has beam splitters to make an action of transistors in such a way that optical activities or involved in modifying the flow of energy. Now, there is another important point that I want to talk about here is that if I take a classical computers having a long range of transistors in them, every transistor that we have in classical computer is independent of every other transistor. So there are, say for example, 10 transistors. 10 transistors, the function of 10 transistors, they are independent of each other. They're doing their job, but they are independent of each other. But that's not the case when you talk about the quantum computer, because in case of quantum computer, we have quantum entanglement. What does that mean? That means if we have two quantum particles entangled with each other, they are going to communicate. There's transformation of information between these two quantum particles, even if the two quantum particles are very very far away from each other. So entanglement. I mean. Albert Einstein never supported the process of quantum entanglement because it was violating, in a sense, the concept that there cannot be anything that can move with the speed greater than that of speed of light. So they came up with a paper, EPR, and in that paper they tried to discourage uh, the reality of quantum entanglement. But nowadays we see that people are taking Nobel Prize in the field of quantum entanglement, and it seems that it's a reality that you can have two quantum particles, and you can have an interaction between these two quantum particles such that the influence on one quantum particle will certainly make a change on the another quantum particle, even if that quantum particle is at infinity with respect to the first quantum particle. So here the interaction is involved. It's not the case of classical computers where there's no interaction at all. Every transistor is independent of every other transistor. Here, if an atom is entangled with another atom, the two atoms are connected with each other. What Einstein called as spooky action. They have some kind of interaction, and because of that, but that interaction is not measurable. We cannot measure that information. But there is that state of transfer of information between these quantum particles. So this makes it very crazy when we think about a system in which all the quantum particles are entangled. That means if the rat that I was talking about, if the rat is the part of this quantum system, and there is a complete set of connection between all entangled paths, and and finally, what's going to happen? What's going to happen after that when you have to reach uh, the other side is the interference. The third important part of quantum computer is interference. So, what is interference? If we talk in a very, very, very physical sense, if we have two state of waves, they can interfere with each other, and this interference will lead to some kind of superposition, and there can be point of states in the space where the interference will take in such a way that the resultant will be a minima, the resultant will vanish, and there can be a state where the two waves will superpose with each other in such a way that you will have the result on the other side. So if I take this system as having these infinite number of interference patterns taking place, but what could be the final way? Because finally the rat has to choose the best path. In this case, the rat has not actually to make all those possible zeros and ones and go all the way to reach its foot here on the other side. That's not the case here. That in this case, all the tracks are there, and whatever has to be rejected, that will be rejected via interference. And I should say that the core cause of that should be the destructive interference, and the single pathway that will lead this rat to its prey in the best possible way. That single track will be the result of constructive interference of the superposition of some of the states that will take the rat to its final destination. So, with this, I would like to end this presentation.